All right, team, strap in, lock in, let's get going. We're learning about compound angles today. Compound angles, and then tomorrow is going to be Delta Math Day. There's Delta Math that's just dropped for a variety of topics that you've seen in my absence. I'll be here to support you on all the lessons that I missed tomorrow. All right, so let's go. Compound angles is when we have like, situations like this is theta plus beta or something like that. We got like two angles in there. So let's take a look. We're going to be applying cast rule today. We need our exact values from special triangles. We're going to be using the unit circle, and we're also going to be learning our compound angle formulas. Okay. Sometimes you want an exact value for an angle, but we don't have a special triangle for that angle. But these formulas will still allow you to get exact values for the trigonometric ratios in these cases. So let's take a look. All right, here they are. So these are also the sum difference identities. So these are a type of trigonometric identity. These might show up in a very challenging trigonometric identity proof. Okay, these you will want to write down somewhere. If you brought a Sharpie and you haven't already written that cute guy or girl's phone number on the back of your arm, these could go there. Okay, should last for a few days. A couple showers, you should still be able to see your compound angle identities. Maybe put it on a post-it note and then put it on your bathroom mirror next to your affirmations. You are lovable and capable, and sine A plus B is equal to sine A cos B plus cos A sine B. Say it every morning. How are we going to remember these? Just build a formula sheet. Take the L on that bonus mark I'll offer you if you memorize this stuff. If you get the tattoo in time, I'll still give you the bonus mark. Not for Sharpie. If you tell me that's a tattoo and then a few weeks later it washes off, I'm not going to say, yeah, I already had the laser tattoo removal surgery, Mr. Jennings.
It's a temporary tattoo.
Yeah. That would be super awesome. You could probably sell those online, actually. I think that's the smartest thing I've ever heard you say, and I've known you for a while.
I appreciate it. I feel it.
Yeah. But no, seriously, like math cheat sheet, temporary tattoos, like come on, that's a great idea. That would do well on Amazon.
You should start selling.
Yeah, that's really good. And this is one of them. Just like screenshot that. Put it on your arm. Yeah. So let's look at some mnemonic strategies. Okay, people have had a chance to write these down. That's great. Take a picture, whatever. The people who take a picture, you're pretty much like saying, there's no chance I'm going to remember this. I think if you write it down, you're going to have a much better chance of remembering it, and you think about it a little bit. So just like, people know what Socrates said when people said, oh, we write stuff down and it will help people's memory. You know what Socrates, yeah, what did he say?
I was like really pissed because he said it's actually going to hurt people's memory.
Yeah, we used to have to remember everything. Now you're writing things down? People will put all kinds of knowledge in their head without truly understanding it. That was what Socrates thought. So now the phone, it's even worse, right? Your memory's going to get all flabby. So you want to practice your memory. So here's one thing that I would do. What would you do to remember the sine ones? The ones that correspond to sine A plus B or sine A minus B? You flip the sign. How do you mean? It does. Addition is here corresponding to addition, and subtraction is corresponding to subtraction. So that looks kind of like a strategy we could use. So sines kind of are like, if I know there's three primary trigonometric ratios, but if there was one that was more primary than the others, it would be sine, right? So sine, we've got A plus B, and then we do sine A cos B plus cos A sine B. So you always have sine cos, okay? And then sine A minus B, we still got sine cos. So that's pretty good. And then cosine, it's kind of doing you dirty here. It's like, you know, how the x always lies and the y always tells the truth. Well, this one, it's opposite. But cosine's a little easier because we just go cos cos minus sine sine and cos cos plus sine sine. So those would be some of the things I'd notice if I wanted to be someone that was earning bonus marks. Okay, let's keep going. All right, so let's say we were given this problem. Should we work out each one independently and then solve it? What would the shortcut be if we wanted to use a shortcut here? See anything you recognize from the last 10 seconds? Eva?
The pattern's like the last one, cos A minus B.
Yeah, so I remember that cosine always lies. So this is like cosine of 7 pi on 12 minus 5 pi on 12. And then I go up to my cheat sheet that I had temporary tattooed on my body, and I'm like, yup, that matches that pattern perfectly. And so then I just do this, right? This is so much easier. 7 minus 5 is 2. So this is cosine of 2 pi on 12, which is a very fancy way of saying cosine pi on 6. And now what? Huh?
Do the sign as well, right?
Do the sine as well.
We have to do.
Oh, we have this pattern, right? Cosine A minus B.
That's cosine A plus B, right?
No, this is cosine A minus B because cosine lies. Yeah, so this is cosine A, cosine B minus sine A, sine B. And I figure that this is just like a little bit kinked, so there, that's now square. Okay. What? Plus, thank you. Yes. So that matches this pattern. So actually it's much easier to evaluate this side than it is that side. There's like 4 operations I need to do here, 4 triangles that I need to think about, blah, blah, blah. Okay, so I can just go straight to cosine pi on 6, and then I imagine my triangle. Pi on 6 would fit here. Pi on 3 is up here, and that's a 90-degree angle. And so this is the 2, 1, root 3 triangle, so we are root 3 on 2. So this one is root 3 on 2. Wasn't that easy? Much easier than evaluating all of these pieces and then doing your arithmetic and having so many chances to make an error there. Well, let's keep going. You want to try this one, or you want to see me do this one? Try this one.
Yeah,
Try it. Looks something like this. Oh, so if I have pi on 6 over here, it goes with pi on 3. Like together it should add up to pi, because together they add up to 180, and 180 equals pi. I don't so much need that other angle, but I'm just writing it in just to remind you of what they look like. So, and it also gives us a chance to have this conversation. A sixth plus a third is a half. So then we add that to the other 90 degrees, which is pi on 2. Pi over 6 goes there, because we end up with 3 pi on 18, which is the same thing as pi on 6. And pi on 6 is 1/2. Sorry, sine of pi on 6 is 1/2. To be honest, Kunal, when I see pi on 6, I am doing a little sneaky conversion in my head to 30 degrees because I'm more comfortable in degrees. But I need to be comfortable in working in radians too, and I'm pretty darn comfortable. But it's a little bit like, you know, these pants aren't your favorite, so you wear your favorite underwear underneath. No one needs to see your favorite underwear. I don't need to show you the degrees thinking that's happening in my head. I just show you my radians thinking.
I've never heard that saying before.
It's not a saying. I make these metaphors up on the fly. Okay, let's go. All right, any questions about that one? We want to be able to recognize our identities and apply them to make our lives easy. That's the goal here. So you try this one. Go. All right, so what's the identity? Which identity do we use here?
Yeah.
Cosine of A plus B is the correct identity. Good. And then when you add these two things together, what do you get?
Pi on 7.
Pi on 7 plus 4 pi on 21? You get pi on 3, yes, good. So your work could look something like this. So I write down the identity that I'm using. So that means all of these is the same thing as this expression. You add pi on 7 together with 4 pi on 21. Pi on 7, we multiply here by 3 and 3. And then we add together with 4 pi on 21. And last time I checked, 3 plus 4 is 7. So 7 divided by 21 is indeed 1 on 3. And then cos pi on 3 is 1/2. And I just imagine my pi on 3 angle there, it's 60 degrees. But I don't tell you that. That'd be obscene. Okay, questions about this one? Keep going? Yeah, let's keep going. So, what if we had a problem like this and we wanted sine 11 pi on 12? We want to know the exact value of that. Gee, how could we use what we just learned to solve for the exact value of something like this?
We do the other way around.
So what would the other way around look like in this case?
Can you set it equal to 0?
No, it's not itself equal to 0. We don't have a variable there, we're just evaluating, really. So we're not like solving an unknown.
It's an ugly number.
It's, well, 11/12 is not that bad. It's like, oh, it's 11 o'clock. How close to noon is it since midnight? You know, people talk this way all the time. It's 11/12 the way to midnight.
I just don't like the number 11 in general.
Oh.
Just a weird looking number. It's just 2 words. Yeah, but like other
Well,
numbers.
yeah, okay, we could talk about that for a while. But I happen to know, like, I could try some stuff, right? I could do maybe like 3/4 plus, like, I don't know, maybe 1/3, and what do I get? That would give me, well, that's not quite it. That's too big. But what if I did something like, how does that look?
Better.
It's a little better, eh? And I happen to know these, right? So this would be the same thing as sine of 2 on 12 pi. So pi on 6 plus 9 on 12. That's the same thing as 3/4. So 3 pi on 4. Okay, we're going to use this identity to solve it. So I just have to like use my creativity or my just number sense to break down this fraction into recognizable pieces. Quarters and sixths, or halves, are basically what we can use to use our special triangles. And then we just carry on. So this is equal to sine of pi on 6 multiplied by cosine of 3 pi on 4 plus, because sine is telling the truth, like we still use that plus, cosine of pi on 6 that's a 6, not a 0, multiplied by sine of 3 pi on 4. And now we just evaluate. Sine pi on 6, what is it? Be faster. Cosine 3 pi on 4, what is it? So visualize the unit circle. Here is 1/4 pi. Here is 1/2 pi. Here's 3/4 pi, 135 degrees. Okay? So I have my 1/√2 triangle, but this is negative. So we are -1 on √2. This wants to get really fluent. You want to be able to find these values pretty quick. Okay? Cosine pi on 6. Cosine pi on 6, who's got it? Sine pi on 6 is 1/2. Cosine pi on 6 is a little different. It's root 3 on 2, yeah. And so you're imagining your triangle laid down the long way. And this is root 3, and that's 2, and that's where you get your cosine there for cosine pi on 6. Okay, and then sine 3 pi on 4. We're still here, 3 pi on 4. So we notice here sine is going to be positive, so we're CAST. Sine is still positive over there. And it's the same as cosine, but the opposite sign, so it's multiplied by 1 on root 2. Okay? Put these together. So this gives us negative 1 on 2 root 2 plus root 3 on 2 root 2. And so that simplifies nicely to root 3 minus 1 over 2 root 2. I'll take that for full marks, no problem. Anyone want a like a bonus quarter point on the whole test? Yeah, Thomas? Yes, multiply top and bottom by root 2 to rationalize our denominator for style points. Okay, this would be for style points. So just do that for style points because I say so, not because it's a requirement, but we should know how to do it. So that gives us 8 on the bottom. No, it doesn't. It gives us 4 on the bottom. Ouch. 4. And this is like root 8. That's what I was thinking. That's where I got that error. Okay. And then over here we have root 6 minus root 2. And there it is, simplified. Okay? Go. See, get out of here. Go. Check the rest later. Okay. Try this one. 13 pi on 12. How can we bust this one apart? Bust 13 pi on 12 into recognizable pieces where we have a triangle that go with it, huh?
9 over 12 and 4 over 12.
9 over 12 and 4 over 12 works. Or 3 over 12 and 10 over 12 both work. Multiple solutions are available. I'm going to use Connor's because he was really fast with that. That was really good. So that would be, this is the same thing as cosine of 9 pi on 12, which is 3/4, plus 4 pi on 12, which is 1/3. Okay, this is different than the way I did it earlier today. So we just use our identity for cosine of adding the angles together. Cosine, they go together. So I have cosine 9 pi on 12. I'm just going to write 3/4 pi times cosine of pi on 3. Okay. Minus, because this one is cosine and it lies, or whatever you want to say, sine of 3 pi on 4, sine of pi on 3. Check your cheat sheet, make sure it's the correct identity. Remember at the beginning of the lesson where I said I didn't have them memorized? You were all there at the moment where I memorized them. I memorized them by trying to remember. It's like, that's like the kind of thing you do to get good at things, is you just try it. Like, I want to deadlift 500 pounds. Try it. Try it every day for a year. Eventually that barbell will move. Yeah. Okay, so now we just do it. There. So there's our exact values for those things. Work them out, and you end up with minus root 3 minus 1 over 2 root 2, multiplying by root 2 top and bottom, and we get a very similar expression to the one we had in the last problem. Negative root 2 minus root 6 all over 4. Okie doke. Keep going. We got a couple other problem types that we want to get to. So I'm going to skip over this one because you voted for fast lesson. And I'm already showing that I can't quite do that. Well, this one is, let's just figure out what identity you would use. So go ahead. We want negative pi on 12. What would be the add or subtract, multiply or divide that you would use here?
Can you
Multiply and divide is red herring. Don't do that. I'm joking.
positive 3 over 12 and negative 4 over 12?
Awesome. Yeah. 3 pi on 12 minus 4 pi on 12 is like so direct and excellent. Yeah, so that's what you would do there. Great. And then work it out on your own time. What about cosecant 5 pi on 12?
Would you include both sine and cosine elements or no?
Cosecant?
It's the reverse of. Is it the reverse of cos?
They always have a co in each pair. Cosecant already has its co,
Okay.
so it doesn't need cosine. It just needs sine. It's sine. Okay, so this is 1 over sine of, how do you make 5 pi on 12? Sorry, I'm not very patient. You said you wanted it fast.
Yeah.
2 plus 3 is 5. And these are both, so this is 1 over sine of pi on 6 plus pi on 4. And then you just work out 1 over sine pi on 6 cosine pi on 4 plus sine pi on 4 cosine pi on 6. It's just a reciprocal of that whole thing. That's all. That's it. Evaluate it and then keep flip change. I'm going to do the whole thing because it's a good enough example that we should see what it looks like. 1 over sine pi on 6 cosine pi on 4. So sine pi on 6 is 1/2 times 1 on root 2 plus 1 on root 2 times root 3 on 2 equals 1 over 1 plus root 3 over 2 root 2. Okay. So Kenzie, what would I do now? Would I give this as my final answer?
No,
What would I do?
you factor the, or you multiply by the root, like,
Multiply by root 2? Yeah, but I've got 1 over 1 plus root 3 over
Just do
2 root 2. Sorry?
flip it.
Yeah, keep flip change. So I just flip the bottom. So then I could give this final answer as 2 root 2 over 1 plus root 3. Now, supposing I got to 2 root 2 over 1 plus root 3, what do I do if I want to have a rationalized denominator? Multiply top and bottom by root 3? Do you want to try it and see that it doesn't work, or do you want me to just tell you it doesn't work?
Just tell me.
Doesn't work that way.
How about it?
How do I rationalize the denominator in this case? I multiply top and bottom by 1 something root 2. So we multiply here by the conjugate. The conjugate, sorry, by root 3. So 1 minus root 3, top and bottom. We're going to multiply. How did I know to multiply by 1 minus root 3? Well, you're going to see that this creates a difference of squares and totally eliminates all of your irrational numbers on the denominator. This is called multiplying by the conjugate. And the conjugate just means if you have like a plus b, the conjugate of that is a minus b. And so if I multiply top and bottom by the same thing, I'm multiplying by 1. But we're going to see that this gives us a very nice simplification. Watch. On the top, we'll have 2 root 2, that's this times this, minus 2 root 6. Okay, so that's root 2 times root 3 is root 6, and then 2 times that is 2 times that. Okay, now let's do the denominator. 1 times 1 is 1. 1 times minus root 3 is minus root 3. Positive root 3 times 1 is positive root 3. See how those will cancel? And then root 3 times negative root 3 is negative 3. So then we get 2 root 2 minus 2 root 6 over minus 2. Nice, eh? And then just divide top and bottom by minus 2. So we end up with root 6 minus root 2. Done, final answer. So now you know that the cosecant of 5 pi on 12 is exactly equal to root 6 minus root 2. These are the type of things that mathematicians get mildly excited about, and having like exact values to these weird trigonometric expressions. Let's keep going. Okay, we got another one that's very similar. We're going to skip it. Okay, there's extra practice. We're going to skip it. But we want to get to stuff like this. Okay? If we had something like single trigonometric ratio, determine the exact value, it's not that bad. Right? You're going to recognize that this is sine 5 pi on 36 plus 10 pi on 36. Okay? Because we have the formula for sine A plus B up there. Okay? Why what? Why 10 pi on 36? Because I didn't have the patience to write another line, so I'm just creating my common denominator ahead of time. Okay? And then we get this is equal to sine 15 pi on 36, which is a fancy way of saying sine 5 pi on 12. 5 pi on 12, well, that would be the same as sine 3 pi on 12 plus 2 pi on 12. And then we'd be back to using the sum of sines compound angle formula. And it would be very much like the problems we had above, just multi-step. Comfortable with that one? Or is there some discomfort on one like this? Okay, let's keep going. We still have more doing to do, right? Like this, we have to now use that formula. It's sine pi on 4 plus, sorry, sine pi on 4 times cosine pi on 6 plus cosine pi on 4 times sine pi on 6. And then you evaluate and put your stuff together. Not following? Okay. I'll do examples of that like that tomorrow. Okay, let's try this one. This one is like more a thinking problem, more tricky. If we want to find sine A minus B, but we know that tan A is 12 on 35, and sine B is 20 on 29. What do we have to do here? Okay, first of all, we know that they're positive acute angles A and B. So get out your unit circle and think about tan A. Okay, tan A, this is opposite over adjacent. So A looks something like this, where you have this is 12 and this is 35. All right, and so now we're going to be interested in, well, what is H? So H squared would be equal to 12 squared plus 35 squared. 12 squared is 144. 35 squared is 1225. And that's H squared. So when we add those together, H squared is equal to, I'm mildly excited because I don't know this Pythagorean triple, 9, 6, 3, 1369, 1369. Is that, no, it's not 66 squared. Sorry, 36 squared.
35 point.
Yeah, it's 35 gross. Yeah, it's something gross.
Sure, 35 point.
Yeah.
It's 37? 1369?
Is it 37 squared?
No.
Yeah, okay, that actually makes sense. So H is 37.
So I said 7.
Good. Okay, so there's a new, actually I've seen that Pythagorean triple before. 35, 37, 12. Yeah, cool. All right. So there's one of our triangles that we're going to use for A. And then for B, we got to go figure that out. So if sine B is 20 over 29, let's just do this in another color. Pion, pion. 20 over 29, that is opposite over hypotenuse, so it's pretty tall that way. This is 20. This is 29. And this is, we don't know yet. Call it little q. All right? So then we get q squared plus 20 squared equals 29 squared. So q squared is equal to 29 squared is 841. and 20 squared is 400. So then q squared is 441. And wouldn't you know it, it's my favorite number backwards, which is 21 squared. So q is equal to 21. So it's not actually quite as tall as I drew it, but, you know, can't all be perfect. Now, we have the two triangles that we need to build out our bigger expression, right? 37. So we're now interested in sine A minus B in simplest form. So let's just go kind of upwards. We're going to work at the top of the slide here. And I'm just going to write out sine A minus B is equal to sine A cosine B minus cosine A sine B. Okay? And then just put in your values and evaluate. So sine A, we know sine A is, well, here is A, and here is B, so let's just label our triangles so that we know. Sine A is 12 over 37. Cosine of B is 21 over 29. And we're going to subtract that from cosine of A, which is 12 over 37. No, it's not. It's 35 over 37. And then sine B is from down here 20 over 29. Okay, so then we're going to simplify that. 12 times 21 is a big number. 35 times 20 is not that bad. Okay, so 37 times 29. Oof. Okay, would this appear on a non-calculator test? It could, but I'm not going to do that. I'll let you use a calculator for these calculations. That's 703. Is it? No, it's not. I'm very wrong. Don't worry, I checked my work. 37 is 111. 111 minus 37. It ends in a 4. No, it doesn't. 111 minus 7. Wait. Why am I struggling? 37 times 30. Oh, it's 1010. That's what I'm doing wrong. Why is this so hard? I'm right now? Really? Yeah, that looks good. Okay, and then 12 times 21. Yeah. It's too boring to watch me do mental math. I'm also not on my game. 238? Yeah, of course. 238. 12 times 21 equals 252 minus 35 times 20 is 700, so minus 448. And then we check for common factors, but it's very unlikely to have a factor 37 and a factor 29 in that number. Yeah, I don't think they exist. 2, 2, 4, 1, 1, 2. Nope. 1, 2, 56. No, they don't share any common factors. Numerator, denominator. So that would be our final answer there. Okay, this example I'll show you tomorrow. There's a Delta Math that landed, and there are some practice problems. So get going. Try those. By shorter lesson, I mean the lesson doesn't really spill too far into tomorrow, and we have time to do some work now. Any questions, hit me up by email or find me in class. Bye for now.